The topic of our discussion is Switched Reluctance Motor, abbreviated as SRM. Before getting into detailed discussion of this machine, we'll discuss the historical background of this machine. We all know very well, in the year 1820, Oersted discovered electromagnetism. After discovery of electromagnetism, the first constructed machine was SRM by the great scientist Davidson. But the machine was not popular on those days due to the lack of high-speed digital controllers. Whereas today the electronic industry has grown very much. Many high-speed digital controllers are available. Therefore, more researchers are concentrating on this machine and also believing that in future this SRM may replace the induction machine discovered by Tesla in the year 1880. Right. We'll discuss the construction of SRM. This SRM is a kind of special electrical machine. It is neither DC machine nor AC machine, but it is said to be electronically switched machine. The cross-sectional view of 4-phase 8x6 SRM is shown here. It is a doubly salient singly excited machine. That is, both stator pole and rotor pole are protrude into the air gap, and stator alone carries winding. That is why it is said to be doubly salient and singly excited machine. The number of phases of the machine is decided by the number of pairs of poles present in the stator of a machine. Considering this configuration, there are 8 poles on the stator, which is equal to 4 pairs. Therefore, the machine is said to be 4-phase machine. 4 phases are identified as phase A winding, phase B winding, phase C winding, and phase D winding. Each and every phase winding is divided into 2 coils. So for an example, when A phase is considered, A phase winding is considered, which is divided into 2 coils A and A dash, and which are placed on the diametrically opposite poles and also which are connected together, powered by external DC source through power controller. This is how phase windings of the machine is excited. Considering rotor of this machine, rotor is completely free from windings or magnets. Considering the operation, for an example, when A phase winding is excited, stator pulse behaves like an electromagnet and pulls the rotor towards the excited phase. That is, the rotor will get moved towards A phase and it will get aligned with the stator poles. At this aligned position, reluctance is minimum, whereas inductance is maximum. We know very well inductance is inversely proportional to the reluctance. Therefore, at this aligned position, reluctance is minimum, whereas inductance is maximum. This is the inductance corresponding to the aligned position. When phase B winding is excited, rotor pole moves away from the stator pole and inductance starts decreases because reluctance will get increased. A similar operation holds good when phase C and phase D windings are excited. From this, it is very clear that sequential excitation of the phases causes continuous rotation. For this operation, whatever we have stated, rotor rotates in a clockwise direction. That is, initially we have excited A phase winding, following that we have excited B phase winding. Therefore, rotor rotates in a clockwise direction. Instead of energizing phase B winding after A phase winding, if we energize D phase winding after A phase winding, the same rotor rotates in the anti-clockwise direction. So the sequential excitation of the pattern or the commutation sequence of the that is the sequence at which we are exciting the phase winding decides the direction of rotation of the machine. Right. The electromagnetic torque contributed by the individual phase is expressed by means of the expression which is shown here, where T is the electromagnetic torque, which is equal to half I square dl by d theta. From this expression, it is very clear that torque is directly proportional to square of the current. That is, irrespective of the direction of the current, the torque is always positive. And the sign of the torque is decided by dl by d theta. If dl by d theta is positive, it is corresponding to motoring operation, and dl by d theta is negative, it is corresponding to generating operation. That is, To operate the motor, to operate the machine as a motor, phase winding should be excited during this rising inductance region where dl by d theta is positive. If dl by d theta is positive, torque contributed by the machine is also positive, therefore machine operates as a motor. When the phase winding is excited during the falling inductance region where dl by d theta is negative, torque developed is also negative, which means it extracts energy from the wind turbine. This is how the machine operates as a generator. From this discussion, it is very clear that the switch reluctance machine is having the capability to operate as a motor as well as generator. Thank you.